Okay, so next we will start transferred electron devices. So, in this type of devices we do not use any p-n junction. Typically one type of semiconductor materials, either n type or p types are used, and n types is preferred since in n types mainly it is associated with electrons mobility, and we have seen that electrons mobility is higher than the hole mobility. Then how it can generate millimeter wave signal, we will see. This type of devices associated with two conduction bands, and because of this two conduction bands they are associated again with two different types of effective mass, and which gives two different types of mobilities. So, electron velocity they becomes different, and due to which a single given device or given structure, it will give you differential resistance, and this differential resistance can give you millimeter wave signals. So, how we will see later. So, let us see first some basic characteristics of these transferred electron devices. So, we do not use any p-n junctions here, as I said. So, some type of materials with same type of materials with different grading profile, and typical materials are gallium arsenide, indium phosphide, CDT. So, silicon, germanium, these conventional materials are not used. Why? I am going to discuss later. Normal operation at low electric field, and it will provide negative resistance at high electric field. We call it hot electron effect. Most popular applications in oscillators to generate microwave and millimeter wave signals. So, if we keep on increasing the applied biasing voltage for this type of devices, initially current increases, after a saturation value then it decreases, and if we further increase the applied voltage, after that it follows the conventional resistance property, then current again increases. It happens due to this type of variation of velocity, carrier drift velocity, with the applied electric field. In this chart we are comparing the carrier drift velocities for different types of materials and for electrons and holes. So, if I see that for silicon, both for electrons and holes, carrier drift velocity it increases with the applied electric field, and at some point it reaches a saturation value. But for gallium arsenide electrons, the carrier drift velocity first increases, reaches a maximum value, and then it decreases. So, since carrier drift velocity decreases, then current it will decrease with the increasing voltage in this region, and it will give negative resistance. So, right hand side picture it shows a typical gun diode using gallium arsenide layer. So, it is using a chunk gallium arsenide in between two metals. These metals are simply used for connections. One is used as cathode and another one is used as anode. Then the threshold fold, where the velocity it changes its slope, it depends on length of the material, type of the material, and also temperature. J.B. Gunn, he was doing one experiment using this group 3 group 5 material in IBM lab, and he discovered the characteristics of these transferred electron devices, and that is why sometimes it is called Gunn diode. So, let me discuss his experiment, what he was doing. That time it was well known that gallium arsenide device is noisy. Whenever we send some RF signal through any gallium arsenide device, then it provides noise. So, what was Jebigan's intention? He investigated the source of noise, and what he found out, it is shown here in this plot. He sent one square wave through a gallium arsenide sample of amplitude 16 volt, and on time is given by 10 nanosecond. So, 10 nanosecond, that means it belongs to megahertz, and what he received at the output, you can see some noise like signal, it is superimposed on the given signal. Now, if we zoom in this noise part, it looks like a very good sinusoidal signal with a time period of 0.2 nanosecond, that belongs to microwave frequencies. So, the input is a RF signal, whereas the output, it contains both the RF input and microwave frequencies. And also he observed the frequency, this high frequency component generated by the device, it depends on the length of the sample. He used, for this particular example, typical specimen length was 25 micrometer. Now, how a gallium arsenide device, it can generate microwave or millimeter wave signal. So, to understand that, we have to understand the RWH theory, or popularly known as Ridley-Watkins-Hillsum theory. So, it deals with differential resistance. So, let us say we have a sample here shown by this rectangular block. Now, some voltage is applied between the left hand side and right hand side, cathode and anode, and somehow on a given filament, let us say resistance increases. Then most of the applied electric field, it will appear across that high resistance region. It is shown here by this red block here. So, in outside this red block, the electric field value will be much smaller compared to that across this red block, since this red block has higher resistivity compared to other region. Now, this filament having higher electric field, it moves from cathode to anode. We will see why later, and how this high field region is generated. And once it reaches the anode terminal, then suddenly we have high current. At the same time, we have another high electric field region generated at the cathode terminal. So, it keeps on generating, and that is how we have microwave or millimeter wave signal, and the frequency, it depends on the specific specimen length. Similarly, we may have also high current filament. So, where the controlling signal is current. Now, why it happens? This picture, it shows the EK diagram for n-type gallium arsenide. So, this bottom part, it shows the valence band, and this top one, it is showing the conduction band. Now, in addition to this primary conduction band, we have one more valley. The bottom of this valley is little high compared to the previous one. The band gap at 300 Kelvin for gallium arsenide from this valence band to the first conduction band is 1.43 electron volt, whereas the gap between the first and second conduction band, it is 0.36 electron volt. Now, when we apply some voltage between left hand side and right hand side, what will happen? So, electrons will transit to conduction band. Now, if we keep on increasing the voltage, so electrons momentum will increase, or electrons, it will go to higher region of this EK diagram inside the conduction band. Same thing happens for the hole, but this is in the valence band. Now, if the electron kinetic energy is sufficiently high, in that case, if it is more than, let us say, the bottom of the second band, then it will see that there is one empty band available which has lower energy. So, it will jump into the second band, but for that we need to provide sufficient energy to electron. Now, what will happen? The electrons, we have some inside the first band and some inside the second band. Let me show you the next plot. So, you see the when the electric field is less than this E L, where E L we are calling the electric field of the lower valley, and in that case mostly electrons it is in the first conduction band. Now, if we keep on increasing the electric field value, so x axis it shows the kinetic energy, or it shows the momentum k. So, the kinetic energy and momentum it will increase, and let us say E v, this is the E field of the valence band, and E u it represents the E field of the upper valley, the second band. Now, if we keep on increasing the applied electric field, in that case its momentum will increase and some of the electrons it will transit to this second band, second valley. So, what happens here in this case, if I calculate total conductivity of this material, that can be given by sigma, this is equal to E into mu L N L. So, it corresponds to the electrons which are inside the lower valley, and plus we have some electrons in the upper valley also, then we have a contribution mu u multiplied by N u due to the electrons inside upper valley. Now, one interesting thing is that if I compare the effective masses at these two different valleys, this lower valley it is associated with lower effective mass, and this higher valley it is associated with higher effective mass. So, since effective mass of the electron is high, then electron mobility is low. So, that means the electrons in this second conduction band in upper valley, they have lower velocity. So, if we keep on increasing the electric field, more and more electron will transit to this upper valley, and as a whole overall current it will decrease due to the reduced velocity in the second band. Now, a condition, third condition, when the electric field is sufficiently high, so that it is more than the E field of the upper valley E u. So, first band is almost empty and almost all electrons now in the second valley. So, in this case we do not have any contribution or N L equal to 0, and it will behave like a normal semiconductor material. So, again if I keep on increasing electric field beyond this value, this velocity will increase due to increment in k. So, we see then it can happen if only second or this upper valley is present. So, these are some typical popular materials for which the gap energy is given here. For germanium, E g is 0.8 and separation energy between two valleys is 0.18. Typical threshold field is 2.3 kilovolt per centimeter, and peak velocity it is given 1.4 into 10 to the power 7 centimeter per second. For gallium arsenide, these values are 1.43 and 0.36. So, looking at the working principle, then we see that it should have two valleys. Not only that, the separation between the first valley and valence band and the first valley and second valley, it should be different, and for the second case it should be smaller than the difference between valence band and the first valley, otherwise it will not happen. And not only that, there should be a difference of effective mass, so that we will have different velocities for these two different values. So, criteria for negative resistance, then we can generalize energy difference between bottom of the lower and upper values be much larger than VTH threshold value. The separation energy must be smaller than the band gap, otherwise the semiconductor becomes conductor, and electron in the lower valley must have high mobility, small effective mass, and low density of state. Low density of state, that means rate of change of E with respect to k, it should be larger, as shown in this figure. So, if I look at the edges for the second band, second conduction band, you see it is more flat. So, looking at this criteria, silicon, germanium, indium antimony, indium arsenide, gallium phosphide do not meet the conditions, but gallium arsenide, indium phosphide, cadmium telluride, they meet the condition. So, we can use these materials to fabricate any GaN diode or negative resistance device due to transfer electron effect. Now, let me discuss then how we can generate microwave or millimeter wave signal from this type of devices. So, let us go back to the very basic things. So, let us say we have this rectangular block, it shows the schematic N type gallium arsenide sample, and consider the applied voltage is ETH near the threshold. So, in that case, let us say somehow usually due to noise there is accumulation of electrons here in some region. Now, because of that the velocity of this electron it decreases, or the resistance it increases. So, once the resistance increases, in that case we have high electric field. So, we are applying some biasing voltage between left and right hand side, cathode and anode, and because of that we have electric field inside the sample. Initially it is uniform throughout the material, but somehow if there is accumulation of electrons here, so the resistance it will increase, and as a result, then the electric field across this filament it will suddenly increase, and it will keep on increasing because the electron it will start moving to the second band, second conduction band, and now we have a dipole formation somewhat like this, and then because of the applied electric field it also drifts from left hand side to right hand side. So, once it reaches this anode terminal, then suddenly we have high current. At the same time, to keep the voltage at same level, we have a generation of another filament at the cathode terminal, and it keeps on generating, and so as a result we have a series of current maxima, which the separation of these two current maxima it depends on the type of materials and the length of the materials, and we have microwave or millimeter wave signal for that. So, domain's length it is inversely proportional to doping concentration. Now, let us see how a GaN diode is used as a millimeter wave source. It is very popular in laboratory experiment. So, it shows a waveguide based system, and here in top right figure you can see a cutaway view of the waveguide source based on GaN diode. So, GaN diode it is placed inside the rectangular waveguide. On top of it we have the biasing arrangement which will provide that ETH value. And now the resonance frequency or the source frequency, it is determined by a tank circuit. Here it is realized by using a cavity resonator, waveguide cavity resonator. So, you can see left hand side we have one iris. Basically, we have a shorting wall and a slot etched in that shorting wall, we call it iris, and the equivalent impedance looking from the gun, it is inductive, and right hand side we have a sliding short circuit. So, then the resonance frequency is determined by the cavity length from this iris to this short circuit plane, and we have a usually mechanical tuning arrangement, so that we can slide this short circuit position and we can change the cavity length, so that the resonance frequency changes and it will generate sorry, different millimeter wave signals. Now, due to this external arrangement, we have different impedance loading. Usually for the iris we will be facing inductive loading, and we have to cancel somehow the inductive loading. Because of that, a matching screw is used, and it is usually capacitive and it can nullify the effect of this iris. So, you can see the assembly from outside using split block technology, and this bottom left figure, it shows a electron microscope photograph of a GaN diode. You can see the black color gallium arsenide sample in between two copper metals. This copper is used just for connection. Next device is avalanche transit time device. So, in this type of devices, it is associated with breakdown phenomena, avalanche breakdown phenomena, the same phenomena what we see for a PN junction diode at low frequency. In addition to a simple PN junction, here usually a drift zone is intentionally provided, where the electrons can accelerate under given electric field, and it can gain sufficient kinetic energy from that, so that when it will strike any silicon or any semiconductor atom in, and it can break any covalent bond and generate electron hole pairs. So, two basic conditions, they are used in avalanche breakdown condition, and we need a drift zone to accelerate the electrons. So, because of this impact, we call it impact avalanche device. So, some basic properties rely on the effect of voltage breakdown across a reverse biased PN junction, and then carrier impact ionization and drift in the high field region of a semiconductor junction produces a negative resistance at microwave or even at millimeter wave frequencies. Now, depending on mode of operations, we have three different types of popular diodes. The first one is called impact ionization avalanche transit time operation, or simply impaired diode, but the efficiency is very poor, typically 5 to 10%. The next one is trap plasma avalanche triggered transit operation, or trapper diode. Efficiency is little higher, 20 to 60%. And then the third category is barrier injected transit time operation, or buried diode, but the efficiency depends on many factors. So, here we are going to discuss on impaired device. Impaired diodes, mainly they are used as power amplifier, and it can generate even kilowatt order millimeter wave signal, and successfully it has been used at 94 and even as high as 300 gigahertz. So, the before basic operations, here are three different schematic for three different types of impact diodes. The first one is abrupt p-n junction, and you can see p plus n n plus. So, n middle layer, it is lightly doped and it is used as the drift region. Next one, p plus p n n plus. So, this lightly doped p n part, it is used as the drift region, and next one is p plus I n plus. So, I intrinsic layer, this is used as the drift region where electrons will accelerate and gain sufficient energy from the electric field, so that it can break one covalent bond when impact. So, let me discuss about the very basic operation of a p plus I n plus type impact diode. So, we will assume that electric field is high enough inside, so that when the electrons accelerate inside the intrinsic layer and it inside n plus, it will hit covalent bonds and generate electron hole pair, and under high electric field it will keep on impacting, and then we will have more and more electron hole pair generation inside. Again this newly generated electron hole pair, they will again accelerate and they will also create more electron hole pair, and this is, that is why it is called an avalanche procedure. It can produce a negative AC resistance. So, since negative AC resistance, we can have oscillation at microwave and millimeter wave frequencies. So, how it operates? Okay, it will be little lengthy. So, let us take 5 minutes break, then we will start again. Thank you.